Okay, in this video we're going to introduce the concept of acceleration. Acceleration is something that often people know, they've heard of it, but it's sometimes misunderstood and can be a difficult concept to grasp. So let's start with the standard unit. Standard unit is a meters per second or a meters per second squared. You'll see that where we get that in a second. Most simply put, acceleration is speeding up or slowing down. When our speed changes, when your velocity changes, you accelerate. So from that, we can find the average acceleration of an object if we know its velocity at two different points in time and the amount of time that went by in between, or the time interval. So average acceleration, change in velocity over amount of time that goes by. So let's look at an example right away in something that you guys are familiar with. Cars. Cars accelerate, right? Let's say you got your old classic Ford Pinto and it accelerates from 0 to 50 miles per hour in 17 seconds. Very crazy fast there, right? You wanted to find the average. Let's be specific because I'm giving you two end points, 0 and 50. Let's solve this out. Remember, first of all, useful conversion from miles per hour to meters per second. 1 mile per hour is 0.447 meters per second. So 50 miles per hour is 50 times 0.447, or 22.35 meters per second. So I do the conversion. My initial is 0. My initial time is 0 to 17 seconds. So I get an acceleration of 1.3 meters per second squared. Notice I have meters per second is velocity, seconds is time, meters per second, or meters per second squared comes straight from that. Another way to write that is 0.13 G's. Sometimes you hear of a G-force or some such and such plane pulled out of like a 4.5 G turn, or on a roller coaster ride at Great America you went around a 3 G turn. A G refers to an acceleration in relationship to the acceleration due to gravity. So 9.8 is a commonly known number. It'll come up later in the unit, later in this unit, for how fast things accelerate towards the Earth. So 1 G would be an acceleration of 9.8 meters per second squared. So in this case, 1.3 meters per second divided by 9.8 tells me in relation to a G-force, this is 0.13 G's. Nothing that'll really get your stomach churning. All right. What happens if the Pinto then slams its brakes, and thankfully it's able to stop faster at a higher rate than it is able to speed up, and it takes 4 seconds to come to a complete stop after applying the brakes. In this case, the average acceleration is found taking the final velocity minus the initial. So always the change is final minus initial. As a reminder, delta V is V final minus V initial. So I start at 22.35, then I end up at 0 because I come to a stop, and it takes 4 seconds. In this case, I have a negative acceleration, 5.6 meters per second squared, or 0.57 G's. So you're going to feel that, right? Your stomach is going to lurch forward in your body at a faster rate because you're slowing down faster than you're speeding up here. So note this negative acceleration here means that the velocity is decreasing. Doesn't always mean that you're speeding up or slowing down. You can have a negative acceleration and be speeding up. So I don't want you to get stuck with the misconception that negative acceleration is always slowing down. I'll show you an example later in this video of when we can have a negative acceleration but actually be speeding up. It just means velocity is decreasing. All right, another way we can find average acceleration is given velocity and time data. So if you had did a lab or something and you had velocity at certain points of time, and you're able to look and see that there's a similar step up, that's going to tell you it's a constant acceleration. From 2 to 5, from 0 to 1, 5 to 8, 8 to 11. You're always going up by 3 in 1 second of time. So between any of these 2 points, you could find the average acceleration as just the change in velocity over a certain period of time. In this case, it would be 3 meters per second squared. All right, let's do a couple sample problems before we move on. 2 scenarios find the average acceleration. First is Usain Bolt in his gold medal winning world record, whether it was aided by HGH or some other form of performance enhancing drugs, has yet to be proved, but he did go from 0 to 28 miles per hour in 6.25 seconds during that Olympic gold medal run, find his average acceleration. And in a McLaren F1, a car I would love to have and drive to school every day, would actually make my commute a little bit more enjoyable. Not that I'm complaining, but I do live a little farther away than you guys, and this would be nice to have a McLaren that goes 0 to 60 in 3.2 seconds. So pause the video, go ahead and make the conversion and calculate those average accelerations. Okay, Usain Bolt accelerated at a rate of 2.0 meters per second squared, and the McLaren accelerates at 8.4 meters per second squared. So can Usain Bolt outrun a McLaren? No, he would have to get in a Ferrari or some other car that could keep up and possibly win that race of acceleration. Okay, I'm going to pull up another scenario here, one that will help us understand the idea of acceleration and the direction of motion, something that's very commonly misunderstood. So let's go back to our Pinto, and let's look at our Pinto at 5 different snapshots in time. Each one of these times, the Pinto is going to have a certain velocity during a certain clock time. Say we start at a time of 0, and at a certain period of time it's got a faster velocity, then it slows down and turns around and goes backwards. It goes backwards a little faster, and then it eventually comes to a stop. So here is our data. The data just gives us velocities and times. So from this, we're going to figure out what is its acceleration during certain intervals. So as we go from time 1 to time 2, the velocity of the McLaren goes from 5 meters per second. And just to be sure you understand, to the right is positive, to the left is negative. That's our standard way of setting up any problem. It should be commonplace for you to understand that from what you've done in your math classes. So if I wanted to find the average acceleration from 1 to 2, I see that my velocity increases, so my final minus my initial, so this is a positive value in a certain amount of time, gives me a positive acceleration of 6.1 meters per second squared. So I have a positive velocity and I'm speeding up, I have a positive average acceleration. So I'm going to the right and I'm gaining speed, I'm gaining velocity. That is going to combine to give me a positive average acceleration. Now, what happens from stage 2 to 3? In stage 2, I'm moving 27 meters per second. By stage 3, I've stopped and I start going backwards at negative 4.6 meters per second. So if I look at my delta V, negative 4.6 minus 27 over the amount of time that went by from here to here, I get a negative 6.6 meters per second squared. Well, if I start with a positive velocity and I'm slowing down, the negative acceleration here corresponds to losing velocity, right? I start positive velocity, but I lose it, so I'm slowing down, going back to 0, and then actually turning around and going in the other direction. So when I have a positive velocity but I'm slowing down, I have a negative acceleration. I think those are the 2 easiest cases to see, right? If I'm driving down the street and I slam on the brakes, my velocity decreases, you would think that's a negative acceleration. That makes sense. Well, what about from stage 3 to stage 4? In stage 3 to stage 4, he starts at a velocity of negative 4.6 meters per second, and he ends at a velocity of negative 17 meters per second. So he's moving faster, but he's moving faster in the negative direction, to the left. Don't be confused between velocity and speed here, right? The fact that 17 is greater than 4.6 means faster. The fact that it's negative just means the direction, to the left. So where am I moving fastest in all 5 stages? Well, at V2, 27, it's the biggest number. Where am I moving second fastest? At stage 4, negative 17. Remember that speed has to do only with the absolute value, only with the magnitude of the velocity, not the direction. So from 3 to 4, I am actually speeding up because I'm getting faster in the negative direction. But in the negative direction means I'm gaining negative velocity. So I'm going to have a negative acceleration, meaning I'm getting more negative, if that makes sense. So every second that goes by, my velocity gets more negative. Speeding up, negative acceleration. That's one of those really can catch you type sample problems. Finally, from 4 to 5, I'm going negative 17 meters per second, slam on the brakes, come to a stop at 0. So in this case, I do have a negative velocity. I'm moving to the left, but I'm slowing down. So I'm losing negative velocity, if that makes sense. And when I lose a negative velocity, I have a positive acceleration. So 4 different scenarios, 2 with having a positive velocity, speeding up or slowing down, positive or negative acceleration. Then 2 when I have a negative velocity, speeding up means more negative, so I have a negative acceleration. Moving negative velocity, but slowing down means moving towards 0. To get back to 0, I have to add positive velocity or I have a positive acceleration. Very tough concept. Watch this over again if you need to. Think it through in your head. I'll give you a sample problem that'll make you practice this a little bit more. But this is one of the tougher things for you to be able to figure out. So let's do a couple samples here. Let's find the average acceleration for from stages 2 to 4, and then from stages 1 to 5. Slide this back over. So pause. Go ahead and pause the video. Solve for those average accelerations. Okay, from 2 to 4, I started at 27. I end at negative 17. Final minus initial gives me a bigger negative number over the time interval from here to here, negative 5.4. And from 1 to 5, my overall, I start with a positive 5, end at 0, so I've lost velocity. I have a negative 0.38 meters per second squared.